I can multiply both sides with 2ax and get 2 times ax times the change of x displacement. Let me write slower. Delta x is this divided by 2a. The top is the change of x velocity squared. Okay? So if I multiply both sides by 2ax, then I get just the change of x velocity squared. So that's the change of x velocity squared if the external force is a constant. There will be changing force later. Similarly, the change of y velocity squared will be just the same thing because you down enough of x and y, you know you just swap x with y and then you get a thing for y, right? So the change of kinetic energy, which is this, will be 1/2 m. The change of x velocity squared will be 2ax times x displacement. Similarly, the y velocity squared will change by 2ay times delta y. So now you see why we have a factor of 1/2 for kinetic energy. Because when you have constant acceleration, the velocity square will be changed by twice ay delta y. We don't want this factor of 2, so we say kinetic energy have this 1/2, and it can cancel this factor of 2. If you don't have this 1/2 in the definition of kinetic energy, you'll still be fine. You just need to live with an extra factor of 2 here. So we made a choice. We decided 1/2 is a real number that people can remember. So we define kinetic energy as 1/2 mv squared. So we see there's MA and MA is the distribution rule. You multiply a number with a parenthesis, you multiply the whole thing in a parenthesis with the same number. Now, Newton's second law tells you that F equals ma. So what you're looking at here, ma is the x component of the force, and this is the y component of the force. We see to change the kinetic energy of a particle, you need an interesting combination of force and displacement. You need to multiply the same component between them, x with x, y with y, and then sum them together. You are contracting two vectors by pairing their same component, and then multiply the component with component, then add them together. It is too burdensome to write such a long expression, so we define this contraction between vectors as the first as f dot the displacement. This is what we call a dot product between vectors. So you can have multiplication between vectors, but the definition is to multiply the same component and then add them together. Okay? We define it just because you see this is like 6 inch, this is 12 inch, 6 inch is saving a lot of space. Okay? And we further define the dot product between force and displacement as work, called W. Again, I go from 12 inch to 6 inch to 3 inch, so saving a lot of space. And now the whole chalkboard, full chalkboard of work just turned into work will change your kinetic energy. Okay? This is the work kinetic energy theorem. Is it E or O? E. Okay. So the thing that changes the kinetic energy of the particle is the work done on the particle. The work done on the particle is the dot product between force and displacement, which is you pick out their x component, multiply together, and add them with the same thing for y component. Okay? So this dot product has some important properties. I'm not going to go through all of them, I'll just mention them when we need them. Dot product between two vectors, A and B, is defined as taking out the x component of them, multiply them together, and add them with the same thing of y component. And the components are numbered, so if you do this, you get a number. So dot product will contract two vectors into a number. That's what dot product is doing. And here, the work is the contraction between force and displacement. To change kinetic energy, you need to have a force. If I want to change the kinetic energy of this chair, I can't just push it with a force. I need to push it with force for a distance. Then you see now the kinetic energy is bigger. Just a force is not enough. You need to push it for a displacement. Then you get kinetic energy. So the dot product is defined this way. If you draw out the vectors, let's say we put vector B on the x-axis and vector A is making an angle theta with the B vector. Now, what is the x component of B vector if the magnitude is B and it is lying on the x-axis? It's just B, good. How about the y component?
Zero.
Good. So when we look at the dot product between A and B, you just write out the components x, x, y, y, and then add them together. You see, in this case, the y component of B is 0, so the second term disappears. You get the x component of A times the magnitude of B because B is lying in the x direction. Now, x component of A is this guy. This is the x component of A. So if this is A, this is theta, will AX be A sine theta or cosine theta?